Here we are with lecture video 1-1 for AP Physics. We're going to learn about motion in this class, and we have to learn how to represent that motion. So there's going to be a variety of ways that we do that, and let's take a look at how we will. One is to look at diagrams such as this, a time-lapse photography, and you can see exactly what the motion of this bird is. It's not a straight line, it's circular in nature or sinusoidal in nature. And we're going to look at the basic concepts of motion. And there's different types of motion that we're going to study. And you can see here that we're going to look at straight line motion. That's what we do first. Then we do circular motion, projectile motion, rotational motion. And the path that an object takes is called the object's trajectory. Now, to represent this motion, we can either use pictures, as you can see here, or graphs and equations. We're first going to look at pictures, motion of pictures. Motion through pictures. They're called motion diagrams. So what we see here is a time-lapse photography of this skier, and you can get an idea of what this skier's motion is, where the top of the motion is, where they land, and so on. And this is called a motion diagram. Now, we're going to look at a couple simple motion diagrams first, and they're just pictures with evenly spaced time periods. So you can see that this person is going at constant speed because the distance from the first picture to the second picture is the same as the distance from the second picture to the third picture. But this person here, we could tell, is speeding up. You can see the distance between each picture is increasing, and that's because the time between each picture is the same. And here, you can see that this car is slowing down. We're also going to look at two-dimensional motion. This is an object not traveling a straight line, but following this curved trajectory. And we're going to do a quick check here. There's two cars, car A and car B, and both have the same time interval between their photos. Which car, A or B, is going slower? So I want you to take this quiz and decide which one's going slower or faster. Hit car A, you're correct. Now, to make things easier, we're going to use what's called a particle model. Instead of having to draw a picture of the object each and every time, we can use dots to represent this motion. And so instead of drawing a car that's going slower, the car gets closer and closer and closer, we're going to use these dots that get closer and closer. And we can see that the car is slowing down with the dots. The numbers here show the order in which the frames were taken. The same amount of time elapses between each frame and the text, and a single dot is used to represent the object. Now here's another quick check. Two runners jog along a track. The positions are shown at 1 second intervals. Which runner is moving faster? So take this quiz now, please. You picked A, you were correct. Another check. We have two runners jogging along a track. The times at each position are shown. Which runner is moving faster? Be careful. Take this quiz. The answer is both runners are running the same speed, and it's because this time interval is 1 second per dot. This time interval is 2 seconds per dot. They're actually going at the same speed. The time intervals between each dot is different. Okay, so now we're going to take a look at putting numbers on nature. We're going to look at position and time, and we're going to make this more mathematical. These pictures, we need to give them some kind of coordinate axis. And here, because it's moving along the x-axis, we have an x-axis that we're going to use. And we have to number this axis. And depending how the question's written, you put the 0 point at the origin, and then you just have your number line just match what the question says. So the post office defines as 0 the origin of the coordinate system in this particular problem. And it says that the car is 4 miles to the positive direction, or to the right, and the cow is 5 miles to the left, which is the negative direction. So this is our coordinate system, and so we're going to be using this just so to keep track of the motion of objects and the position of objects. So here is a coordinate system that hopefully makes sense. We have a racer, a runner, starting at position 0 and going to the finish line 50 meters away. And you'll notice that it's evenly spaced. The distances are evenly spaced, 10, 20, 30, 40, 50. The x-axis is labeled, and the units that we're measuring is labeled as well. Here the meters is shown. So you want your coordinate axis to look something like this each and every time. And you don't have to draw a person. You can draw dots now. Okay, so We're also going to add time to our timeline. So in the previous slide, you see that we had distances. Now we're going to put in time too. And you can start the time at the beginning of a motion, or you can start the time in the middle, depending on what part of the motion you're interested in. Here we have a car that's moving at a constant speed at first for the first 4 seconds, but then braking and slowing down. Somebody might be interested in the whole thing, the whole motion, or somebody might just be interested in the braking part. So you put the origin where you want to put it. So what happens is, in order to quantify motion, we'll need to consider changes in time, and we call these time intervals. The initial position is called xi, the final position is called xf, and you'll notice that we have all the distances measured here evenly. The x-axis is labeled, the units are labeled, and time is labeled for each dot, so we know what the intervals are. And a time interval is delta t. It measures the elapsed time as an object moves from initial position x1 at time, or position xi at a time ti, to a final position xf at a time tf. Delta t is always positive. Here we're going to look at changes in position, which is called displacement. So we have a final position of 0 meters, initial position of 50 meters or 50 feet. So displacement is the difference between the final position and the initial position. Distance is really just how much you've traveled, where displacement is always from the final to the initial. And so we're going to see that sometimes it's the same number, but other times it's different because displacement has direction associated with it. So our change, delta x, is our displacement. So we have x final, which is 0 feet, minus x initial, which is 50 feet. That gives us a negative 50 feet of displacement. And that negative sign is important. That negative sign means we traveled in the negative direction. So I have a couple questions here just to review what we've discussed. Maria is at position x equals 23. She then undergoes a displacement of negative 50 meters. What is her final position? So think about that. Come up with your answer. And hopefully you get an answer of negative 27 because we have a starting position of 23. We go displacement of negative 50. That means we go into the left 50 meters and end up on the number line at negative 27 meters. Next question is, an ant zigzags back and forth in a picnic table is shown. The ant's displacement traveled and the displacement are. Now remember, displacement and distance are two separate things. The distance traveled is the distance the ant travels here, forward, back, and forward again, that total distance traveled. Where the displacement is simply from where the ant started to where the ant ended. So come up with your answer, see what you think. The answer is negative 30 centimeters for displacement because we started at 40 and ended at 10. So 10 minus 40 is negative 30. But the distance traveled, you kind of had to estimate the distances here and add those three distances up to get a total of 50 centimeters.